We will begin our examination of the conic sections with the parabola and defining it in terms of a set of points, a locus of points. We can define it as the set of points equidistant from a fixed line, which we call the directrix, and a fixed point, which we call the focus, that is not on the line. So the point has to be somewhere other than on the line, as we'll see in our illustration. Here is a parabola that has vertex of 2, -1. The focus would be located at 2, 0, and the directrix at y equals -2. We will start by looking at the definition in terms of the focus and vertex and the vertex and directrix. The vertex would be in the set of points that's equidistant to the directrix and to the fixed point of the focus. The distance between the two will be equal. Now, that is not the real interesting part. The real interesting part is when we go from the focus out to some other point, and then from that point down to the directrix. Well, these distances would be the same. So by the definition of the parabola, we create an equation based on the distance between the 2 points of the focus and the point on the parabola, and then the second distance from that same point on the parabola straight down to the directrix. We will develop this formula a little more formally on the next page, and more in general, with not a set, not an exact point as the 2, 0 like we did here, but in general terms where the vertex we're going to call the general point HK. But before we do that, let's draw a few more lines that describe this definition. Any line from the focus out to a point on the parabola, that distance is going to be the same as this distance from the parabola down to the directrix. And we can go as far out, oops, a little too far from what we graphed, but we can see any of these distances. This is D3 and D4, or if we call this one D5 and D6, those distances are going to be equal. Now let's take a look at how we can derive the equation for the parabola. First of all, just a general picture here, general graph of the parabola. We have our vertex at HK, and the focus would be up here and the directrix down here. The distance between the vertex, by definition, it's a point on the parabola. The distance from the focus to the vertex will be the same as the distance from the vertex to the directrix. Now, we will go ahead and call that some distance P. Okay, so P units from the vertex up to the focus, P units from the vertex down to the directrix. Now, with the notation here then, HK, maybe it's the 2, -1 that we looked at in our previous example, or whatever it might be, those are the coordinates of our vertex, and with this parabola opening up, the focus is directly above that point, so the x value of the focus is going to be the same x value as the vertex. Now the y value, it's going to be k, but we add this value of p to that to get the y value of the focus. So the focus turns out to be the point h and then k plus p. Then as we go down to the directrix is a horizontal line, which is going to be the equation of a line, y equals some number. Well, that number will depend on k as well as p, but the directrix is under the vertex, so we have to subtract p units from k, and this becomes the equation for the directrix. Now, applying our definition where d1, distance from the focus to a point on the parabola, that point we'll call in general xy, is going to be the same distance as the point on the parabola xy down to the directrix. Well, my graphing is not quite uniform, so d1 doesn't quite look like equal to d2, but by definition we will make it that way. And what we have to think about then is, how do we represent those distances? We can do that through the distance formula. d1 is going to equal, well, we can say x sub 2 minus x sub 1 under the radical, so x minus h, quantity squared, and then y minus y sub 1 would be our k plus p, and again that's quantity squared. So a little bit ugly expression there for the difference in the y values, but y sub 2 minus y sub 1 quantity squared, that represents the distance for the first from a point on the parabola to the focus. Now the distance from that point down to the directrix, well, what are the coordinates of the point on the directrix? Well, this is the x value, same x value that this point has, and then the y value, this y value, well, that would be the k minus p, because that horizontal line, y equals k minus p, is the directrix. So any point will have k minus p as the y value. So d2 then, distance 2, square root of the difference in x values, well, x minus the same x value would be 0, plus y minus the y value of the directrix, which is y minus p, or y, k minus p, and then square that. So d1 equals d2, and let's see, we can show that in the equation form here. And then we have a whole bunch of algebra to work through to simplify this. Now D2, we might as well simplify that already. We can say it's that part's 0, so that's going to equal the square root of the quantity y minus another quantity of k minus p, and then that big old quantity squared. Okay, there is the equation of a parabola. Now that's definitely not the form we're used to using. We'll kind of rewrite it, simplify it, and make it much nicer, make it look like a form we're used to. But the equation is representing this parabola. Now lots of algebra. First thing I would do is, well, square both sides. And doing that gets rid of the square roots. So top of the next page we'll write down what's left over. So here we have the equation without the square roots, but we still have quite a bit of work to do. Now in the standard form we're going to see the x minus h quantity squared. So we're going to leave that one alone. It's the other two that we're going to simplify. We'll multiply it out, and we're going to find several things that will combine, cancel out, and so forth. But let's kind of work on each one of these individually. And we'll start with this one, y minus the quantity of k plus p. I guess keep that as a bracket. And that factor squared well, we don't need the square on there anymore. Multiplying this out, we'll have y squared. Now here is where it gets a little more interesting. We've got y times the negative binomial of k plus p plus another negative y times k plus p. So we can kind of shorten that notation. We'll have two of those, so minus 2y times k plus p. And then the last part of FOIL, multiply our last, negative times negative would give us a positive, and then we'll have k plus p quantity squared. So simplifying all of that, y squared minus, now let's go ahead and multiply the negative 2y through the parentheses. So minus 2yk minus 2yp, and let's go ahead and multiply k plus p quantity squared out. K squared plus 2k times p plus p squared. All of that is going to be this expression right here. Now there's nothing we can do to combine any of those terms, but we need to do the same thing to this one and then plug everything back into this original equation, and we'll see lots of things simplifying. So our last trinomial that we need to square, y minus the quantity k minus p this time, square that, and well, again we'll have y squared, and again we'll have minus y times that binomial minus another y times that binomial, so minus 2y times that binomial, and then k minus p, or negative k minus p times another negative k minus p, so we have positive, and then k minus p quantity squared. So, a little more algebra, y squared minus 2 yk, and then plus, we've got a negative times a negative, so plus 2yp, and then our k minus p quantity squared, we'll have plus k squared minus 2kp plus p squared. So all of that goes back up into this equation. We'll have our x minus h quantity squared plus this equals this. Well, let's go on to the next page so we can see what we're doing. Okay, we are ready to start combining like terms. We have the equal sign here, so, well, some things to notice. We've got a y squared. We can subtract y squared from both sides, which those y squareds will cancel out. We can add 2yk to both sides, and those terms will cancel out. K squared, subtract that from both sides. P squared, subtract that from both sides. So what's left is the x minus h quantity squared minus 2yp plus 2kp equals 2yp minus 2kp. Well, we'll add 2yp to both sides and subtract 2kp from both sides. And the left side ends up being x minus h quantity squared. The right side we get 4yp minus 4kp, and we're almost to our standard form. If we factor out the 4 and the p, we'll have 4p times the quantity of y minus k on the right side. So this will be the standard form of our parabolas where the parabola opens up, or in case if it opened down, the p value would actually be negative. Now we have more details to look at here in a second, but that's the standard form equation based on the definition. Distance between the focus and a point on the parabola is equal to the distance from that same point down to the directrix. So to summarize, our standard form for a horizontal directrix, if p is going to be greater than 0, it opens up. P, again, will represent the distance between the vertex and the focus. So if p is negative, we think we go down to the focus. Okay. Now, what about a vertical directrix? With the vertical directrix that flips around our equation, that will give the y part the square. We'll have y minus k quantity squared equals 4p times the quantity x minus h. Our vertex is still hk. P still represents which direction we're going. If p is positive, that means the focus this time is to the right of the vertex. If p is negative, we go to the left for the focus. Now, later on we'll look at some examples of how we use this, but these are major forms that we need to remember. This is where the standard form for the parabola comes from.